Welcome back, tech enthusiasts. Today we're diving into the world of data science to explore the different types of gradient descent. Let's break it down with some clear examples. Now, gradient descent at its core is an optimization algorithm. Think of it like finding the lowest point in a valley when you're blindfolded. You take a step, feel the slope, and decide your next step to go further down. In machine learning, this valley is our cost function, something we want to minimize to make our models more accurate. Understanding how we navigate this valley is super crucial. It's one of those foundational concepts that, once you get it, a lot of other things in machine learning start to click into place. Whether you're training a simple linear regression model or a complex neural network, some form of gradient descent is likely working behind the scenes, diligently tweaking parameters to get closer to the optimal solution. So, getting a solid grasp of its variations isn't just academic, it's practical knowledge that empowers you to build better, more efficient models. Today, we're going to look at three main flavors: batch, stochastic, and mini-batch gradient descent. Each has its own way of calculating that slope and taking those steps, and each comes with its own set of trade-offs in terms of speed, accuracy, and computational resources. We'll unpack what makes each one tick, where it shines, and how it actually works with some straightforward examples. So buckle up, because this is going to be a detailed look into a truly essential data science tool. Alright, so first up, let's talk about batch gradient descent. This one is often considered the most straightforward or perhaps the most vanilla version of the algorithm. The batch gradient descent refers to the entire dataset. That's the key characteristic here. It processes all the training examples simultaneously in a single large batch to compute the gradient of the cost function. It's like trying to get a sense of the entire landscape before making a move. Imagine you have a dataset, say, for a simple linear regression model. We're trying to predict house prices based on their size. Our model is a straight line y equals sign mx plus c, where m is the slope, how much the price increases per square foot, and c is the y-intercept, a baseline price. The cost function, often mean-squared error, measures how far off our line's predictions are from the actual house prices for all houses in our dataset. With batch gradient descent, to update our m and c values, we first calculate the error for every single house in our training set using the current m and ce. Then, we average these errors to get the overall gradient. This gradient tells us the direction of steepest descent for the cost function. Since we want to minimize the cost, we take a step in the opposite direction of this gradient. This process of looking at every single data point before making an update ensures that we get a very accurate estimate of the gradient. It's like asking every single person in a town their opinion before making a community decision. You get a comprehensive view. The path it takes towards the minimum of the cost function is generally very smooth and direct, without a lot of zigzagging. So for our linear regression example, let's say we have 1,000 data points, 1,000 houses with their sizes and prices. Batch gradient descent would calculate the predicted price for all 1,000 houses, then compute the error for all 1,000, and then use these 1,000 errors to figure out the gradient for m and ce. Only after processing all 1,000 data points does it make a single update to m and c. This sounds great, right? A smooth path to the minimum. But there's a pretty significant trade-off computational cost. If your dataset is massive, think millions or even billions of data points. Calculating the gradient using every single example in each iteration becomes incredibly slow and resource-intensive. Each step, though well-informed, takes a very long time to compute. Think about it. Your processor has to churn through every single data point, perform calculations, sum them up, and then finally, you get to make one tiny adjustment to your model's parameters. If you have a dataset that doesn't even fit into memory, batch gradient descent becomes practically infeasible. It's just not scalable for the kind of huge datasets we often work with today. So the update rule for batch gradient descent involves summing up the gradients for all training examples. If theta represents our parameters like m and c, and jth is our cost function, the update looks something like theta equals sine theta, alpha asterisk jth, where alpha is the learning rate and jth is the gradient computed over the entire dataset. This full dataset gradient is the defining feature. One advantage, apart from the smooth convergence, is that it can be easily parallelized. Since the calculations for each data point's error are independent before the summation, you can distribute this work across multiple cores or even multiple machines, which can speed things up somewhat. However, the fundamental bottleneck of needing all data for each step remains. The convergence to the true minimum is also more guaranteed with batch gradient descent, assuming your cost function is convex, like a simple bowl shape. Because each step is based on the complete information from the dataset, it's less likely to get stuck in noisy local minima or oscillate wildly around the optimal point, unlike some other methods we'll discuss. However, this guarantee of reaching the true minimum is usually for convex functions. For non-convex functions, which are common in deep learning, think of a landscape with many valleys and hills, batch gradient descent can sometimes get stuck in a local minimum. It finds a valley, but it might not be the deepest one. And because its steps are so deliberate, it might not have the momentum to escape it. Let's visualize this. Imagine a 3D plot of the cost function. Batch gradient descent would look like a ball rolling smoothly and directly down the steepest part of the surface towards the lowest point. There's no erratic movement, just a steady progression. This visual often helps understand its deterministic nature. The learning rate, alpha, is also a critical hyperparameter here. If it's too small, convergence will be very slow, even with accurate gradients. If it's too large, it might overshoot the minimum and diverge, meaning the cost actually goes up instead of down. Finding the right learning rate is key, and it's often done through experimentation. So, in summary for batch gradient descent, it uses the entire dataset for each update. This results in a stable, direct convergence path and an accurate gradient estimation. However, it's computationally very expensive and slow for large datasets, making it less practical for many modern machine learning applications. It's the slow and steady wins the race approach. But sometimes the race is just too long. It's a good foundational method to understand because it clearly illustrates the core idea of gradient descent. You calculate how off your model is across all your data, and then you adjust your model in the direction that reduces that overall offness the most. The updates are infrequent but high quality. For simple problems with smaller data sets where accuracy of the gradient is paramount and computation time is not a major constraint, batch gradient descent can still be a viable option. Or it's often used as a benchmark to compare against other, more scalable optimization algorithms. It sets the gold standard for gradient quality, even if it's not always the most practical. The key takeaway is that batch means all your data, all at once for every single parameter update. This perfect information comes at the cost of speed, especially as your dataset grows. And in the age of big data, that cost can become prohibitive very quickly, leading us to explore other options. Now let's switch gears and look at stochastic gradient descent, or SGD. If batch gradient descent was about making a decision after consulting everyone in town, SGD is like asking one random person and making a decision based on their input alone, then moving to another random person. The stochastic part means random, and that's the core idea. It updates the model's parameters, using just one training example per iteration. So, instead of calculating the gradient based on the entire dataset, SGD picks a single data point, computes the gradient of the cost function with respect to that single point, and updates the parameters immediately. Then it picks another random data point, computes its gradient, updates and so on. This is a dramatically different approach from batch GD. Consider our logistic regression example. Logistic regression is often used for classification tasks like figuring out if an email is spam or not spam. The model outputs a probability. With SGD, we'd take one email, see if our model correctly classifies it, calculate the error for just that one email, and then adjust the model's parameters, its weights and bias, based on that single instance. The most obvious advantage here is speed. Each update is incredibly fast because it only involves calculations for one data point. You don't have to wait to process the entire dataset. This makes SGD much faster per iteration, especially for very large datasets. You can start making progress and updating your model almost instantly. However, this speed comes with a trade-off. The updates are noisy. Since each update is based on only one example, the gradient estimate can be quite erratic. One data point might suggest moving the parameters in one direction, while the next, very different data point might suggest an entirely different direction. This causes the path towards the minimum to be much more jittery and less direct than batch GD. Imagine that cost function landscape again. SGD would look like a person stumbling down the valley, sometimes going a bit sideways, sometimes even slightly uphill for a moment, but generally trending downwards. This noisy, zigzagging path is characteristic of SGD. It's a much less smooth ride to the bottom. This noise isn't always a bad thing though. For complex non-convex cost functions, like those in deep learning with many local minima, the noisy updates of SGD can actually help the algorithm escape these local minima. Batch GD might get stuck in a shallow valley, but SGD's randomness might kick it out and allow it to find a deeper, better global minimum. So the update rule for SGD is similar in form theta equals sine theta, alpha asterisk j tha xi yi. The key difference is that j is now the gradient of the cost function with respect to a single training example, xi yi, at each iteration I. The parameters are updated after every single example. One full pass through all the training data, processing each example one by one with SGD, is called an epoch. In batch GD, one epoch means one update. In SGD, one epoch means an updates wherein is the number of training examples. This high frequency of updates is what allows it to learn quickly. Because of the noisy updates, the learning rate alpha becomes even more critical for SGD. A common practice is to use a learning rate schedule, where alpha starts relatively large to allow for quick exploration, and then gradually decreases over time. This helps the algorithm settle down and converge more finely as it gets closer to a minimum. The variance in the updates is high, but on average, SGD still moves towards a good solution. It's like taking a random walk that, over time, leads you closer to your destination. The stochastic approximation theory provides the mathematical backing for why this works, despite the per-sample noise. For our logistic regression model trying to classify spam, SGD would process emails one by one. If it misclassifies a spam email as not spam, it adjusts its parameters slightly to be better at catching that type of spam. Then it sees a non-spam email, and if it misclassifies that, it adjusts again. These frequent small adjustments allow it to adapt quickly. One downside, apart from the noisy convergence, is that you lose the benefits of vectorized operations that can speed up computations in batch GD. Processing one example at a time might not fully leverage the capabilities of modern CPUs and GPUs that are optimized for parallel computations on large chunks of data. However, the sheer speed advantage per update, especially for massive datasets where batch GD is too slow to even complete one iteration in a reasonable time, often makes SGD the preferred choice. If you have billions of training examples, waiting to process all of them before making a single update is just not practical. SGD allows you to start learning immediately. The convergence of SGD typically doesn't land precisely at the minimum, but rather hovers around it. Because of the constant noise from individual samples, it keeps oscillating near the optimal point. The decreasing learning rate helps to dampen these oscillations over time, allowing for a closer convergence. So, to recap SGD, it updates parameters using one training example at a time. This makes it very fast per update and suitable for extremely large datasets. The updates are noisy, leading to a jittery convergence path, but this noise can help escape local minima in non-convex problems. It requires careful tuning of the learning rate and often a learning rate schedule. It's a workhorse algorithm in modern machine learning, especially for training deep neural networks, because it makes training on vast datasets feasible. The trade-off is a less stable convergence path, but the speed and ability to handle big data often outweigh this. It's the fast and sometimes erratic, but gets you there approach. The randomness in selecting samples for each update is also important. Typically, the dataset is shuffled at the beginning of each epoch to ensure that the model doesn't learn any spurious patterns based on the order of data presentation. This helps in making the gradient estimates more representative over time. Ultimately, SGD offers a powerful alternative when the cost of batch GD is too high. It embraces the noise and uses the speed of single sample updates to navigate complex optimization landscapes efficiently, making it a cornerstone of training large-scale machine learning models we see today. So, we've seen batch gradient descent, which is accurate but slow, and stochastic gradient descent, which is fast but noisy. This naturally leads to the question, is there something in between? And the answer is yes. Mini-batch gradient descent. This method tries to strike a balance, capturing some of the benefits of both batch GD and SGD. The core idea of mini-batch gradient descent is to split the training dataset into small, manageable batches or mini-batches. Instead of using the entire dataset, like batch GD, or just one example, like SGD, it computes the gradient and updates the model parameters using a small batch of, say, 32, 64, 128, or 256 training examples at a time. This approach offers a compromise. By using a mini batch, the gradient estimate is more accurate and less noisy than with SGD because it's averaged over multiple examples. This leads to a more stable convergence and less oscillation around the minimum. At the same time, it's much faster than batch GD because you're not processing the entire dataset for every update. Let's consider training a neural network, perhaps for image recognition. A neural network can have millions of parameters. Using batch GD would be incredibly slow. Using SGD would mean updating these millions of parameters based on just one image at a time, which could be very erratic. Mini batch GD offers a sweet spot. We process, say, 64 images, calculate the average gradient from these 64, and then update the network's weights. One of the significant advantages of mini-batch GD is computational efficiency. Modern computing hardware, especially GPUs, is optimized for vectorized operations, performing the same operation on multiple data points simultaneously. Mini-batches are large enough to leverage this hardware parallelism effectively, leading to faster computations per example compared to SGD's one-at-a-time processing. So the update rule for mini-batch GD looks like theta equals theta minus alpha times the gradient of J with respect to theta and B, where B represents a mini-batch of training examples. The gradient is computed over this mini-batch. The parameters are updated after processing each mini-batch. If you have in total examples and a batch size of B, you'll have in divided by B updates per epoch. The choice of batch size, B, is a crucial hyperparameter. If B is too small, it behaves more like SGD, with noisy updates and less efficient hardware utilization. If B is too large, it approaches the behavior of batch GD with smoother convergence but potentially slower updates and higher memory requirements per batch. Common batch sizes are powers of 2, like 32, 64, 128, 256, due to hardware memory alignments. Compared to SGD, mini-batch GD provides a more stable convergence path. The variance of the gradient estimates is reduced because you're averaging over a small batch of samples instead of relying on a single sample. This means the parameter updates are more consistent and generally point more reliably towards the minimum. Compared to batch GD, mini-batch GD is much more scalable for large datasets. You don't need to load the entire dataset into memory to compute a gradient, only the current mini-batch. This makes it feasible to train models on datasets that are too large to fit into RAM. The noise in mini-batch GD, while less than SGD, can still be beneficial for escaping local minima in non-convex optimization landscapes, similar to SGD. It offers a good balance between the stability of batch GD and the exploration capability of SGD. It's often the default choice for training deep neural networks. For our neural network training example, using mini-batches means that the network gets feedback from a small group of images before adjusting its weights. This group provides a more representative signal of the overall data distribution than a single image, but it's still processed much faster than the entire dataset. This allows for frequent updates that are reasonably well informed. Learning rate schedules are also commonly used with mini-batch GD, similar to SGD. You might start with a larger learning rate and gradually decrease it as training progresses to help the algorithm fine-tune the parameters and settle near a good minimum. The process for one epoch of mini-batch GD involves shuffling the dataset, then iterating through it mini-batch by mini-batch. For each mini-batch, you perform a forward pass to get predictions, compute the loss, perform a backward pass to get gradients, and then update the parameters. This cycle repeats for many epochs. So, mini-batch gradient descent effectively combines the robustness of SGD with the efficiency of batch processing. It's more computationally efficient than SGD because it can take advantage of vectorized operations and parallel processing. It's more robust than SGD because the gradient is averaged over a small number of examples, reducing noise. It's really become the de facto standard for training large machine learning models, especially in deep learning. It navigates the trade-offs well. You get relatively fast learning, good generalization, due to some noise helping avoid overfitting and sharp minima, and efficient use of modern hardware. The selection of the mini-batch size itself can impact model performance and training dynamics. Smaller batches introduce more noise, which can lead to better generalization but slower convergence in terms of wall clock time due to less efficient computation. Larger batches offer faster computation per epoch but might converge to sharper minima, which sometimes generalize less well. Think of it as finding the right size for your survey group at each step. Not too small that the opinion is unrepresentative like SGD, Not so large that it takes forever to survey everyone, like batch GD, but just right to get a good sense of direction quickly and efficiently. This is the pragmatic approach. In essence, mini-batch gradient descent is the workhorse that powers much of the progress in deep learning today. It provides a scalable and effective way to optimize complex models with vast amounts of data, offering a practical middle ground between the extremes of batch and stochastic gradient descent. It's about finding that optimal balance point. And there you have it. The three main types of gradient descent in data science, each with its unique approach and use case. We've seen how batch gradient descent uses the entire dataset for super accurate but slow updates. Then there's stochastic gradient descent, going one sample at a time for speed but with a much noisier path. And finally, mini-batch gradient descent, which tries to find that sweet spot in between, offering a balance of speed, stability, and efficiency, making it a go-to for many modern applications, especially in deep learning. Understanding these nuances is pretty key because the choice of optimizer can significantly impact your model's training time and performance. There's no single best type for all scenarios. It often depends on the size of your dataset, the complexity of your model, and the computational resources you have available. Experimentation and understanding these trade-offs will help you choose wisely. Hopefully, this breakdown gives you a clearer picture of how each one operates under the hood. It's a fundamental concept, but mastering it really unlocks a lot of power in machine learning. Thanks for sticking around through this deep dive. Don't forget to like, subscribe, and hit the bell icon for more tech insights. See you in the next video.